Hello and welcome to another one of these ADD videos. Today we're going to be looking at this example here, trying to solve it. Right off the bat, you should notice this is methanol. So it's going to be a one reaction. This indicates heat and should drive it towards elimination. Conditions are a little tricky for this, but typically that's what occurs. So, as always, in a one reaction, the leaving group leaves. Again, we know it's a one reaction because this is a weak base and a weak nucleophile. So the leaving group bromine leaves, and we get a heterolytic cleavage in which bromide ion gets all the electrons from this covalent bond between bromine and carbon's left with an empty p orbital, hence the carbocation. Again, this is the same reaction we saw initially for the SN1 intermediate example video. If you saw that, that's why this looks familiar. We're also going to get the hydride shift that we got in that video because we can increase stability by taking this hydrogen, it's not drawn here, that completes a octet for this carbon, and move it over here. And if we move it over here, we fill this empty p orbital and leave this one empty. And the result, when we do that hydride shift, is tertiary carbocation, because it's bonded to 1, 2, 3 other carbons. Again, you're going to get some inductive effect to share the burden of this plus charge, and you're going to get some hyperconjugation of the methyl groups. Actually, this is an ethyl group that help to stabilize this carbocation. So that's why it's the more stable it is. The more carbons attached to this cation, the more stable it is. Resonance is more stable than all of them. So now we can either do substitution or elimination, but because of this heat symbol, then we know we're going to favor elimination. The result is we're going to have multiple possible reactions take place. The solvent, remember it's a solvolysis reaction, is going to act like a base. So we're going to remove a hydrogen from an adjacent carbon, one of these adjacent carbons. All right, so let's label them 1, 2, and 3. And what we're going to do is we're going to use Zatsev's rule to determine which is the major product. Zatsev said that more stable is determined by more substitution on either side of double bond. Yes, this is good, no? So what I said there is that the more substituted you are on either side of the double bond, the more stable you'll be, and result in the major product. So if I remove H1, I get this right here. If I remove H2, I get this alkene here, and H3 gives you that alkene. So if you look at the substitutions, this is using Zatsev's rule. This is tri-substituted, okay? Instead of a hydrogen here, here, and here, we have 3 methyl groups. This is only di-substituted, the ethyl, the methyl. We have 2 hydrogens not drawn here. This is also di-substituted, similar scenario. Actually, this is the same compound, so. But I still wanted to show you what happened when you removed either one of those. All right, so the more stable one is the one that's tri-substituted, and that would be your E1 reaction with a hydride shift. I hope I've explained everything all right, enough for you to practice these problems. The only way you're going to get familiar with this stuff is to do as many of these as you can. So practice, practice, practice. Thanks for watching, and have a great day.